Good morning, everyone. I'm excited to welcome you all today. Today's presentation is titled 100 Most Important Electrical and Solar Project Quality Questions with Answers. I'll be guiding you through some key questions and insights that are crucial for ensuring quality in electrical and solar projects. Over the next few slides, we'll cover a range of topics from design, installation, to maintenance best practices. So, let's get started and make this session both informative and engaging. Welcome to this overview of our presentation. Today, we'll be covering key topics related to the quality of electrical and solar projects. This includes the entire process from design, installation, testing, to safety measures. Our goal is to ensure that every stage meets high standards, which ultimately leads to successful and safe project execution. I'm Varun Vijay, the electrical manager, and I'll guide you through these important aspects. As we move forward, keep in mind that maintaining quality at each step is crucial for the overall success and reliability of our projects. This foundation supports our commitment to delivering safe, efficient, and sustainable energy solutions. Welcome to the section on electrical basics. Let's start with Ohm's law, which is fundamental in understanding how voltage, current, and resistance relate to each other. It's simply V equals I times R, meaning voltage equals current times resistance. This helps us analyze and troubleshoot electrical circuits effectively. Next, in India, the standard frequency of electricity supply is 50 Hz. That means the current alternates 50 times per second, which is important for the proper functioning of our electrical appliances and systems. Moving on, the unit of power we use is the watt. It's a measure of how much energy is being used or transferred over time. When we talk about energy consumption or capacity, watts are what define that. Now, let's discuss the power factor, which is represented by cos phi. This is a measure of how effectively electrical power is being used. A higher power factor indicates more efficient use of electricity, which is crucial for reducing energy waste. And speaking of efficiency, improving the power factor helps reduce losses in the system. When the power factor is closer to 1, less energy is wasted as heat or other forms of loss, leading to better overall efficiency. All these fundamentals are key to understanding how our electrical systems work and how we can optimize them for better performance and cost savings. Let's take a closer look at the basics of solar PV technology. First, the primary function of a solar panel is to convert sunlight directly into direct current or DC electricity. This is the fundamental process that powers solar energy systems. Next, you'll see the terms VOC and ISC. VOC stands for open circuit voltage, which is the maximum voltage the panel can produce when no load is connected. ISC, on the other hand, is the short circuit current, representing the maximum current the panel can generate when the output is shorted. Understanding these helps us gauge the panel's performance under different conditions. Moving on, MPPT, or maximum power point tracking, plays a crucial role in optimizing energy extraction. It ensures that the system operates at the point where it produces the maximum possible power, especially as sunlight conditions change throughout the day. Now, regarding the panel capacity, a 540 WP panel typically consists of 144 cells. The WP stands for watt peak, indicating its maximum power output under standard test conditions. Knowing the number of cells helps in understanding the panel's size and efficiency. Finally, the temperature coefficient of -0.35% per degree Celsius tells us how the panel's performance decreases as the temperature rises. For every degree increase above standard test conditions, the panel's efficiency drops slightly, which is important for designing systems in various climates. All these points tie back to our overall goal of designing efficient, reliable solar power systems. And with that, I am Varun Vijay, your electrical manager, ready to assist further. Now, let's move on to cable laying and termination. First, it's crucial to maintain the bending radius at 12D, which means we should keep the bend radius at least 12 times the cable diameter. This helps prevent damage and ensures the cable's integrity over its lifespan. Next, using cable tags for identification is essential. Proper tagging makes future maintenance and troubleshooting much easier, as you can quickly identify each cable's purpose and connection point. Glands for sealing are also important. They provide a secure and waterproof seal at termination points, protecting the cables from dust, moisture, and other environmental factors that could compromise their performance. We also need to conduct insulation resistance testing using a megger. This test checks the cable's insulation integrity before energizing the system, ensuring there are no faults or weaknesses. And speaking of tests, the insulation resistance should be greater than 1 megaohm per kilovolt. For example, if you're testing a 3 kV cable, the IR should be above 3 megohms. This is a good indicator that the cable is properly insulated and safe to energize. All these steps are vital to ensure a reliable and safe electrical installation, which ties into our overall focus on quality and safety standards in every stage of the project. Let's talk about the earthing system. First and foremost, the main purpose of the earthing system is safety. It's designed to protect both people and equipment from electrical faults. When we talk about safety, having an effective earthing system helps prevent dangerous electric shocks and reduces the risk of electrical fires. Now, an important technical aspect is the earth resistance, which should be less than 1 ohm. A low-resistance path to earth ensures that fault currents can flow easily, quickly dissipating and minimizing hazards. Achieving this requires good quality materials and proper installation. Speaking of materials, we typically use GI or copper rods for earthing. Copper is highly conductive and resistant to corrosion, making it ideal for long-term reliability. GI rods are also common and cost-effective, but they need proper treatment to ensure durability. Next, we have neutral earthing. This involves connecting the neutral point of the transformer or generator directly to earth. It helps stabilize the system voltage during faults and provides a clear path for fault currents, which facilitates protective device operation. Finally, equipotential bonding is crucial. It ensures all metallic parts are at the same potential, reducing the risk of electric shocks. By connecting various conductive parts to the earthing system, we create a safe environment where potential differences are minimized. Overall, these elements form the backbone of a safe and reliable electrical installation. As we move forward, remember that proper earthing isn't just a technical requirement. It's a fundamental safety measure that protects everyone involved. Lightning protection is a crucial aspect of safeguarding our structures and electrical systems. On this slide, we'll discuss the Lightning Protection System, or LPS. This system is designed to safely direct lightning strikes away from sensitive equipment and people. The main parts of an LPS include the air terminal, which is the visible point that attracts the lightning, and the down conductor, which safely guides the lightning current to the ground. A key principle here is the striking distance principle. Essentially, it means that if an object is within a certain distance from a lightning strike, it's at risk. Proper design and placement of our protection system help mitigate this risk effectively. We also have surge devices, or SPDs, which are used to protect electrical and electronic equipment from voltage surges caused by lightning strikes. They act quickly to divert excess energy and prevent damage. And it's important to note that these systems and devices should comply with standards like IEC 61640-311, which ensures reliability and safety. Remember, the goal here is to integrate these protection measures seamlessly into our overall safety strategy, minimizing damage and ensuring the safety of everyone involved. Let's take a closer look at the inverter and SCB quality. First, SCB stands for String Combiner Box, which is a key component in connecting multiple solar strings efficiently and safely. One of our main priorities is achieving an efficiency of over 98%, ensuring minimal energy loss and maximum power output. Polarity check is another critical aspect. It helps us verify that all connections are correct, preventing potential issues down the line. Fuses are incorporated to protect the strings, Think of them as safety valves that safeguard against overcurrent or short circuits. Additionally, the IP65 rating indicates that these components are highly resistant to dust and water ingress, making them suitable for outdoor environments. All these features together highlight our commitment to high-quality, reliable solar power systems. And of course, I'm here to ensure that everything functions smoothly, Varun Vijay, your electrical manager. Let's take a closer look at some of our key quality checks. First up is the torque test. This is crucial because it ensures all fasteners are tightened to the specified torque, which helps prevent future issues like loosening or failure. Next, we have visual inspection. This might seem simple, but it's incredibly important for catching any surface defects, misalignments, or other visible issues that could affect quality or safety. Now, you might hear us mention NCR, which stands for Nonconformance Report. This is a formal way of documenting any deviations from our standards or specifications. When we identify a nonconformance, we don't just note it. We take corrective actions to fix the problem and prevent it from happening again. Speaking of which, corrective action is all about addressing the root cause of a defect or issue once it's identified. It's a vital part of continuous improvement. Alongside that, we also focus on preventive action, proactively identifying potential problems before they occur, so we can maintain high-quality standards across all processes. All of these checks and actions tie back to our overall goal, ensuring the reliability and safety of our products through thorough quality management. Thank you. Safety and standards are the foundation of our work, so let's go through some key points. First, PPE, or personal protective equipment, is absolutely essential. It's our first line of defense against potential hazards on site. Wearing the right PPE helps us stay safe and compliant with safety protocols. Next, we have IS 3043, which pertains to earthing. Proper earthing is critical for safety, as it prevents electrical shocks and ensures that any fault currents are safely directed to the ground. Then there's IS 732, the standard for wiring. Following this standard ensures our wiring is safe, reliable, and capable of handling the electrical loads without risk of short circuits or failures. Moving on, IS 10028 deals with transformers. Adhering to this standard guarantees that transformers are built and maintained to high safety and performance criteria, which is vital for the reliability of our power systems. Finally, for solar installations, we follow IEC 62548. This standard covers the safety and performance aspects specific to photovoltaic systems, ensuring they operate efficiently and safely over their life cycle. All these standards are interconnected. They help us build a safety culture and ensure our projects meet the highest quality and safety benchmarks. It's about protecting ourselves, our team, and the infrastructure we work on. Today, I want to walk you through some of the critical testing and commissioning procedures we perform to ensure electrical systems are safe and reliable. First up is the polarity test. This is a fundamental step where we verify that all connections are correct, ensuring that live and neutral wires are correctly identified and connected. It's essential because a wrong polarity can cause serious safety issues and equipment damage. Next is the continuity test. This helps us confirm that the electrical pathways are complete and unbroken. Basically, we check that current can flow seamlessly through the circuits without any interruptions, which is vital for both safety and functionality. Then we have the HOTO test, or high potential test. This one involves applying a high voltage to the system to make sure there are no insulation failures or leaks. It's a sort of stress test that helps us identify potential weak points before the system goes into operation. Following that is the Megger test, which is a specific type of insulation resistance measurement. It allows us to assess the quality of insulation over time, ensuring that it remains effective and that there's no deterioration that could lead to faults. Finally, thermography. This is a non-contact technique where we use thermal imaging cameras to detect hot spots in electrical equipment. Hotspots can be early indicators of issues like loose connections or overloaded components, so catching these early helps us prevent failures. All of these tests are interconnected in the broader scope of ensuring our electrical systems are safe, efficient, and ready for operation. And keep in mind, I'm Varun Vijay, your electrical manager, here to oversee this process and make sure everything runs smoothly. Let's walk through the HOTO process, which is a critical step in project completion. First, we have the handover takeover, or HOTO, itself, which marks the official transfer of responsibility from the construction team to operations. It's essential that this process is smooth to ensure all systems function correctly from day one. Next, we need to ensure all required documents are prepared, including detailed reports and drawings. These documents serve as the backbone for future maintenance and troubleshooting, so accuracy and completeness are vital. Once everything is compiled, these documents must be signed off by all relevant parties, confirming that everyone agrees the work has been completed as per specifications. This mutual agreement helps prevent any disputes later on. We also conduct punch point inspections, which involve checking every detail to identify and rectify any deficiencies or incomplete work. Think of it as a final quality assurance step before commissioning. Finally, we carry out commissioning tests to validate that all electrical systems are functioning properly and safely under real operating conditions. These tests are crucial to ensure the system's reliability and safety before handing it over for operational use. All these steps, handover, documentation, sign-offs, punch points, and commissioning, are interconnected and reinforce the overall quality and safety of the project. So, by following this process diligently, we ensure a seamless transition from construction to operation, setting the stage for smooth, ongoing performance. Now, let's take a closer look at some common site observations that we've encountered. First up is poor cable dressing. This often happens when cables are not organized properly, which can lead to issues like difficulty in maintenance, potential damage, or even safety hazards. Proper cable management is essential for both safety and efficiency. Next, we have loose earthing. When earthing connections are not secure, it can cause electrical faults or even pose safety risks. Ensuring that earthing is solid and reliable is crucial for protecting both personnel and equipment. Moving on, missing gland is another common observation. Glands help to seal and protect cable entries, preventing dust, water, or pests from entering. Missing glands can compromise the integrity of the installation, leading to potential damage or failures. Then, there's damaged MC4 connectors. These connectors are critical for solar panel connections, and any damage can affect the overall system performance. It's important to regularly inspect and replace any damaged connectors to maintain system efficiency. Finally, missing tagging refers to the absence of labels or identification on cables and equipment. Proper tagging helps in easy identification during maintenance or troubleshooting, saving time and reducing errors. All these points highlight the importance of diligent site management and quality control. As we move forward, keeping these observations in check will ensure a safer, more reliable, and efficient installation. Let's take a moment to go through some key documentation terms that are essential for our project. First, we have RFI, which stands for Request for Inspection. This is a formal request made to verify that work or materials meet specified standards. It's a critical step to ensure quality control early on. Next is ITP, or Inspection and Test Plan. Think of this as our roadmap for inspections and tests throughout the project. It helps us plan, organize, and ensure all required checks are properly scheduled and documented. Then we have MAR, which stands for Material Approval. This document confirms that the materials used meet project specifications before they are installed. It's vital for maintaining quality and compliance. Moving on, FAT, or Factory Acceptance Test, is conducted at the manufacturer's facility. It's where we verify that equipment or systems perform correctly before they are shipped to the site. This step helps us catch issues early and avoid delays later. Finally, we have SAT, or Site Acceptance Test. This is performed once the equipment arrives at the site. It confirms that everything functions properly in the actual operating environment, ensuring the system is ready for handover. All these documents form the backbone of our quality assurance process. They help us keep track, verify compliance, and ensure that the project progresses smoothly and meets all standards. As we move forward, paying close attention to these documentation points is crucial for a successful project. Today, I'll be discussing some of the essential tools and instruments we use in electrical maintenance and testing. First up is the clamp meter, which allows us to measure current flowing through a conductor without disconnecting it. This makes our work safer and more efficient. Next, we have the multimeter, a versatile device that measures voltage, current, and resistance, helping us troubleshoot a wide range of electrical issues. We also rely on the megger, which is a specialized insulation tester used to check the integrity of cables and insulation systems, crucial for ensuring safety and preventing faults. The torque wrench is another important tool. It helps us apply the correct amount of torque when tightening bolts and connections, preventing over-tightening or under-tightening that could cause problems later. Finally, the thermal imager allows us to detect hot spots and abnormal temperature rises in electrical equipment. This is vital for predictive maintenance and avoiding unexpected failures. All these tools are integral to our work, enabling us to diagnose, maintain, and ensure the safety and reliability of electrical systems. They connect to our overall theme of proactive and precise electrical management. Welcome to Slide 16, where we focus on our quality philosophy. First and foremost, we believe in doing it right the first time. This means paying attention to detail from the start to avoid rework and ensure quality. Next, we follow IS and IEC standards, which serve as our benchmarks for safety and performance, ensuring everything aligns with international best practices. It's also crucial to verify and record our work continuously. This step helps us maintain accountability and traceability, so we can track any issues back to their source if needed. Traceability itself is a core part of our philosophy, enabling us to follow the entire process and ensure consistency throughout. Finally, we emphasize quality plus safety. High-quality work must always go hand in hand with safety measures to protect everyone involved and uphold our reputation. All of these points come together to reinforce our overall commitment to excellence, reliability, and safety in every project we undertake. Let's walk through some of the key electrical calculations that are fundamental to our work. First, we have power, which is calculated as voltage times current times power factor. This formula helps us determine how much electrical power is being used or supplied in a circuit. Next, energy is simply power multiplied by time, giving us an idea of how much energy is consumed or produced over a period. Then there's current, which can be found by dividing power by voltage times power factor. Understanding this helps us size our conductors and protect our equipment properly. Voltage drop is another critical calculation, obtained by multiplying the current by the resistance of the wire. This tells us how much voltage is lost as electricity travels through the cables, which is vital for ensuring proper operation. Finally, we have efficiency, calculated as the output divided by the input, multiplied by 100 to get a percentage. This metric helps us evaluate how effectively our systems are performing. All these calculations are interconnected and essential for designing safe, efficient, and reliable electrical systems. They form the backbone of our engineering practices and tie into the overall theme of optimizing electrical performance. Now, let's take a closer look at solar module testing. First, we have the visual check, which is the initial inspection to identify any obvious physical damages or defects on the module's surface. This step is crucial because it helps us catch issues like cracks, discoloration, or broken cells early on. Next, we perform the flash test, where we simulate sunlight to measure the module's electrical output under standard conditions. This ensures the module is performing as expected. Moving on, The EL test, or electroluminescence test, allows us to detect microcracks or other internal defects that might not be visible to the naked eye by visualizing the module's internal structure using special imaging techniques. Then, there's the IR test, or infrared test, which helps identify hot spots or damaged areas that could lead to performance loss or safety concerns. Lastly, we check the VOC and ISC, which stand for open circuit voltage and short circuit current, respectively. These measurements confirm the electrical characteristics of the module align with the specified standards. Overall, these testing steps are integral to ensuring the reliability and efficiency of the solar modules, supporting our commitment to quality and safety across the project. I'm Varun Vijay, Electrical Manager, and I hope this gives you a clear understanding of how we thoroughly evaluate each solar module before deployment. Let's take a closer look at the DC side checks that are essential for ensuring system reliability and safety. First, we have polarity verification. It's crucial to confirm that the positive and negative connections are correctly identified to prevent any reverse polarity issues that could damage components or cause safety hazards. Next is string continuity. This involves checking that the entire string of modules or panels is electrically continuous, ensuring there are no open circuits that could disrupt the system's performance. Moving on, fuse condition is a vital point. We need to inspect the fuses to ensure they haven't blown or deteriorated over time, as a compromised fuse can lead to system failures or safety risks. Fourth, the SPD test, which stands for Surge Protection Device Test. This is important to verify that the SPD is functioning properly to protect the system against voltage spikes and surges, especially during thunderstorms or grid disturbances. Lastly, torque tightness. Proper torque on connections and terminals is essential to maintain good contact and prevent loose connections, which can cause arcing or overheating. All these checks are interconnected and form part of our overall strategy to maintain system integrity and safety. By thoroughly conducting these checks, we can identify potential issues early and ensure our system operates smoothly and safely. Now, let's move on to the AC side checks. These are critical steps to ensure the safety and proper functioning of our system. First, we check the inverter output. It's essential to verify that the inverter is delivering the correct voltage and current, as any irregularity here can affect the entire setup. Next, we perform a Megger test on the AC cables. This helps us identify any insulation resistance issues, preventing potential short circuits or failures down the line. Then, we move to earth continuity. Ensuring a solid earth connection is vital for safety and for proper system operation. Without a reliable ground, there's a risk of electric shocks or equipment damage. After that, we inspect the panel interlink. This step confirms that all connections between panels are intact and functioning correctly, maintaining system integrity. Finally, we conduct relay tests. These tests verify that protective relays are working as intended, which is crucial for system safety and fault management. Remember, each of these checks plays a key role in ensuring our system is safe, reliable, and efficient, aligning perfectly with our overall goal of delivering a robust and secure electrical setup. I'm Varun Vijay, Electrical Manager, and I appreciate your attention to these important checks. Now, let's look at the importance of maintaining quality and some practical tips to do so. Poor work can lead to serious consequences like loss, failure, or even fire hazards, which we definitely want to avoid. To prevent these issues, I recommend inspecting your work daily. This helps catch problems early before they escalate. Recording tests diligently is also crucial, as it provides a documented trail and ensures accountability. Make sure to close NCRs, or nonconformance reports, promptly so no issues are left unresolved. Keeping the work area clean is another simple yet effective habit that supports safety and quality. And of course, always prioritize safety at every step. Remember, these tips aren't just about compliance. They're about protecting our people, our projects, and our reputation. I'm Varun Vijay, your electrical manager, and I encourage everyone to stay vigilant and committed to quality in every task. Thank you all for your attention today. I'd like to leave you with a final thought. Quality is not an act, it is a habit. This emphasizes that maintaining high standards shouldn't be a one-time effort, but a consistent, ingrained part of our daily work. As professionals, especially in fields like electrical engineering, it's essential that we develop this habit of quality in everything we do. When quality becomes second nature, it leads to better safety, more reliable results, and ultimately, greater success for our projects and organization. So, let's remember that excellence isn't just about a single act. It's about cultivating a mindset and routine that uphold our standards at all times. Thank you once again for your dedication and commitment.